Okay, so welcome you all to this lecture, and we would be discussing about 8051 microcontrollers architecture. On the screen, you could see that I have shown the architecture or a brief block diagram form of architecture of 8051. Uh, it could be divided into three parts. So this part, let me call it part A. Let me take a different color. Okay, so this part is your CPU, or where all the uh, instructions are executed. And then we have this part, which is the memory part. And then these are the IO ports of 8051. Okay, so let's start with the CPU. So it has got an ALU, arithmetic logic unit, and you must be knowing that arithmetic logic unit performs the arithmetical and logical operations. And since it is an 8-bit microcontroller, so it performs 8-bit arithmetic and logical operation. Uh, just to uh, write, make things a bit clear, let me take one instruction which is called add instruction. ADD, add, and as the name suggests, it is adding. And let me write a comma r naught. Okay, so what this instruction is doing, adding the content of a and r naught. Now what is a and what is r naught? So let us go back and see here. So I think there is small mistake here. This is a, not b. This is a. So a is a register, b is a register. We know that we require some memory space for for uh, storing the instructions and storing the results of the various operations. So A is a register. Register is nothing but a set of flip-flop. Okay, set of flip-flop. Flip-flops. So there are 8 flip-flops. So it is an 8-bit register, and it is also called accumulator. Accumulator. So this is one of the most important uh, register of 8051, because uh, it almost is everywhere in the instructions of 8051, because the accumulator, it holds the first operand, and the result of the operation gets stored in accumulator A. Okay, and then we have another register, which is B. B is important in the sense that B is also a register, and it is the only register which is used in multiplication and division operation. No other registers uh, is used along with A in multiplication and division. Okay, so I was telling you this instruction add. So add A comma R naught. This is a single instruction in 8051, which basically is doing addition of the content of A and content of R naught. R naught is again a register. Okay, it is a general purpose register. We will talk about it later. Just think that it is a register, 8-bit register, and some numbers are stored in R naught, and similarly some numbers are stored in A. The number size would be 8-bit. okay, in both the registers. So for example, if A is say 10H and R naught is say 25H, okay. So if I give this instruction, let me take A equals to 10H and R naught is having 25H, then the the first operand is A, okay. So this 10H is stored in A, and the second operand is R naught, and 25H is stored in R naught. After this execution of this instruction, add A comma R naught, what would be the result? Result would be 36H. Okay. So this value 36H would be stored in A. That means the content of A would be modified, and now 35 would be there in A after this instruction. Before this instruction, A was having 10H, R naught was having 25H, but after this instruction, A will have 35H. Similarly, if I write another instruction, sub is an instruction which subtracts, uh, say something is in A and something is in B. So whatever is in A get updated after this instruction, and the result of subtraction gets stored in A. So that is why A is a single most important register in 8051, and the first operand and the result of the operation gets stored in A. Okay, I hope it's clear. And B, so I told you that multiplication MULAB and DIV AB. So mul and div, these two are also instruction, and by name itself you can make it out that mul will be doing multiplication and div will be doing division. So mul AB basically multiplies the content of A and B, and as I told you that in mul and div operation, B is always involved. Okay? These two registers are always involved, A and B. We cannot have A R naught in mul operation. Okay, we have only A and B involved in multiplication and division. So that means when you intend to use multiplication and division, you have to store the operands in A and B. Okay, and div AB means A content of A is divided by B. We'll discuss what happens during the execution of these instructions in detail when we'll be discussing the various instruction set of 8051. Right now, just I am talking about these two registers, A and B. Okay, register A and register B. A is called accumulator, and B is a register which is used in multiplication and division operation. Okay. Okay, and one more thing I forgot to tell. In this multiplication and division operation, since you know that A is an 8-bit number, B is also containing an 8-bit number. So when you multiply these two, definitely the result will not be 8-bit. Okay, so it would be a higher bit number. So 16-bit number is there. Then the 16-bit number is stored in A and B both. Okay, how it is stored I will tell you. And similarly, in division operation, after the division is performed, quotient is stored in A. The quotient of this division is stored in A, and the remainder is stored in B. Okay, so this was just something about the registers A and B. Now let us talk about this something called PC, program status. PC is program counter and DPTR, and this is data pointer, and then we have another register called as PSW, program status word. So we'll be talking about these three in a bit detail. Let's start from say program status word. We can start from program status word. Program status word. PSW. So this is one of the SFR which is available in 8051. SFR implies special function register. Special function register. Okay. There are around 21 SFRs in 8051 for various operation. Okay. And these SFRs, we have a complete lecture dedicated to understand the various SFRs in 8051. So I won't be going into the in depth of these SFRs. I was just talking about this program status word. This SFR is basically a flag register of 8051. What is a flag register? You might not have studied 8085 microcontrol processor. Actually, we used to teach 8085 earlier before this course was introduced. And anyway, we will be, I will tell you what is a flag register. You see, whenever there is an operation, so there is a result after every operation, be it addition operation, subtraction, or multiplication, division, or any logical operation. Okay, any operation, any execution of an instruction is carried out, then there are two things that happen. One is result, which is generated. Okay, and then the second thing is the status of the result. So what is meant by the status of the result? Status means actually there are various things in the result itself, say whether it is positive or negative. Okay, say you are performing a subtraction operation. After subtraction, are you getting a positive number or a negative number? This is one of the thing. Then how many ones are there in the result, whether it is odd or even. Okay, and similarly these things are there. Again, if you are adding two numbers, is there any carry or not? Say two 8-bit numbers are getting added, so it may happen that the sum of two will generate a number which is higher than 8-bit, isn't it? So that means there should be some carry number that needs to be taken care of. So all these things are could be seen in the PSW register. And when we look into it in detail, we'll see how it looks like. Okay, now let us see another register, which is the program counter, PC. The program counter. So program counter, okay. Says this program status word, was 8-bit register. Okay. While program counter and DPTR data pointer. One is program counter, another is data pointer or data pointer, whatever you like to call. data pointer. These two are also SFRs and they are 16-bit registers. So you might be wondering how 16-bit register come when we are dealing with all 8-bit registers and 8-bit data. Actually, two 8-bit registers are combined to form a 16-bit register. Okay, because the address address of the external ROM and external RAM, they require how much? 2 to the power 16 address locations are there. Okay, so for that you require 16-bit register, isn't it? So what is program counter? Program counter is an SFR. It is 16-bit long, and it points to, the important thing is, it points to the address of the next instruction in the program. Okay, so let me again use another program counter. It points to, or it stores the address of the next instruction in the program. So you are writing some program, so that program needs to be stored somewhere. There should be some address of those instructions which you are writing, isn't it? So say this instruction is being executed, so program counter will now points to the address of the next instruction. Okay, why it is necessary? So just to make one of one use of it. So whenever there is a interrupt and you are executing the program, and I told you that whenever there is a interrupt, the control moves from the main program, this is the main program, to interrupt service routine, and there the program, subprogram, whatever you call is there, it is executed, and the control shifts back to this next instruction. So how will 8051 remember where it left the main program? So that is done by the program counter. It stores the next address of the next instruction, and uh, the when interrupt has been serviced, control moves back with the help of this program counter. Okay, so please remember, what is program counter? It stores the address of the next instruction in the main program. Now come to DPTR, the data pointer. Okay, DPTR, it consists of two 8-bit registers, DPH and DPL, the higher 8-bit and the lower 8-bit registers. Okay, and what its role? So the data pointer, it actually holds the address data in data memory. Okay, so let me write it down here. It gives, or it stores, the address of the data. Fine. So data itself is 8-bit. Say for example, it is stored somewhere in external RAM or external ROM. So that address would be 16-bit wide, where it is stored. That data is stored. Data itself is 8-bit, but it is stored in somewhere in RAM, ROM, external say RAM or external ROM. So that address would be 16-bit wide. Okay, so that address is stored in DPTR. Fine. And now why it has got two components? You see, it may be internal RAM also, and in internal RAM, the address size is 8-bit. We'll see shortly how, because it is 128 byte long and there are 2 to the 7, okay, memory locations that can be addressed. So only 8-bit is required to access those addresses. So you can use the lower 8-bit only to access the address of the internal RAM. So whatever be the case, the important point is that DPTR actually stores the address of the data, 8-bit data. Fine. So let's move ahead now. So this now CPU part is over. Okay. Now let's move to this memory part. So one more thing you could see here, there are buses that are coming from these registers. This is an 8-bit data and address bus. This is 16-bit address bus. Why it is 16-bit address bus? Because I told you that PC and DPTR are 16-bit registers. Okay. And they point to the address. PC point to the address of the next instruction and DPTR points to the address of the data. So that 16-bit data needs to be transferred with the help of the 16-bit address bus. Similarly here, A, B and PSW both are, all three are 8-bit registers. So they carry 8-bit data and at times 8-bit address also. So 8-bit data and address bus. Okay, fine. So now let's move to this uh, part of the architecture, which is the memory part. Okay. I would be dealing with it again, the memory organization of 8051 in detail in another lecture. Organization. Right now I would be telling in brief about the memory organization in 8051. So I had already told you in my previous lecture that memory in 8051 can be categorized into 4 types. There are internal RAM and internal ROM, and we have external RAM and external ROM. Internal RAM, what was the size? 128 bytes. Internal ROM, 4 kilobytes. External RAM, 64 kilobytes. External ROM, again 64 kilobytes. Okay. So this we have already seen in the previous lecture. Now let us look how this memory is distributed. So RAM has 128 bytes. So let me just represent it here. Okay, so it starts from, now you see that since there are 128 bytes or 128 memory locations, okay, 128 bytes or 128 memory locations. Each byte has got 8 bits. Okay, so how much uh, bit or byte is required to access these 128 bytes. So 128 means 2 to the power 7, isn't it? So 7 bits are required. Okay. So you use 8 bit or 16 bit. Definitely we don't have the provision of 7 bit uh, register. We have registers either of size 8 bit or 16 bit. So that means we can use 2 to the power 7 or 128 bytes of otherwise 256 byte of memory location available, or memory addresses available rather. So 00, it will start from 00H, then 01H, then 02H, and go on till what would be the last uh, address. This is 128. 128 bytes. 128 locations are there. So what would be the last? To know what is the last, you can just do one thing. So 00H, if you write it in binary, so this much. Okay, 0000 and 0000, then 0000 and 0001, this one. And then we have 0000, 0 and 0002, and so on. And now 2 to the 7 means there will be 7 ones. So 4 ones here and 3 ones here, and then 0. In binary representation, 128 is this, isn't it? So that means this is your F, okay, and this is 7. So that means the last memory here is 7FH. Fine. This is about the address. Now data would be 8-bit data are there in these. Similarly, when I talk about internal, this was internal RAM. If I talk about internal ROM, so internal ROM, let me again draw it in the same way. Okay, so 8-bit data here and 16-bit address. Now 16 bits are required. Now 4 KB, 4 KB. So how much memory will it take? 4 KB. This size would be 4K kilobytes. That means 4,000 memory addresses, 4K memory addresses, not 1,000, 4K memory addresses are there. Okay, so it will start from, and definitely not, we cannot use 8-bit now. We have to use 16-bit register, but not all 16-bit would be occupied in the address. Okay. So 4 means it is actually 2 to the power 2, and K means 2 to the power 10. So that means 2 to the power 12 bytes. So 2 to the 12, we have to represent it here. Okay. And we have to start with definitely 16-bit register. So 0000H, then 0001H, and so on. What would be this last address? We can apply the same approach. Let me open a new window here. So 0000, 0000, 0000. This is binary representation of what I have written in hex. This was for 0000H. And what would be 0001H? So all zeros here, all zeros here, all zeros here, and here we will have 1. Fine. So for 2 to the power 12, if I go on like this, so 12 ones would be there. 1, 1, 1, 1, 1, 1, 1, 1, then 1, 1, 1, 1. How much? 4, 4, 8, and 4, 12. So this would be 0, 0, 0, 0. So this would be last address location for the uh, ROM, internal ROM. And this, so if you write it in hex, so 0, F, 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 X. This would be the last address of the internal ROM. Fine. Now, similarly, you can find for external ROM also and external RAM. And that would be very easy because it will go start from 000H and it will utilize all, since it is 64 KB, 64 KB. So 64 is 2 to the power 6 into 2 to the power 10, and it give you 2 to the power 16. So that means the full utilization of the 16-bit registers, 8-bit and 8-bit. Okay. So you by this method you can actually find out what would be the starting and the end address of the various memory locations in 8051 for internal RAM, ROM, and external RAM and ROM. Fine. Now, okay, so this completes your memory part. This memory part is completed. Now come to this part, which is very simple, the IO part. So IO ports, I have already discussed about them. There are 4 IO ports, each having 8 pins. Okay, and one of them is not multiplexed. Rest of them are multiplexed, and one thing you see here, there's a latch that I have connected before this. What is this latch? Latch is basically a flip-flop, set of flip-flops. You see, actually, this data bus or address bus, which is coming to the ports, they carry data, but unless and until that data is latched, that data is latched, or it is stored somewhere, not exactly stored, but latched somewhere, we cannot expect to see that data uh, after some time. Just to take an example, say you have to say you have to you are using a calculator. Okay, you do one operation, 8 into 5. So 40 is displayed on the LED or LCD, whatever you are using. So that means you want that number 40 to be displayed there for a while, unless you press some other button. Okay, you do not want that 40 should just blink away and go. So for that you need to use this latch, and they are basically flip-flops which stores the data. Okay, which latches the data. So this is about the IO port of 8051. And then I had told you that there are various SFRs in 8051 which would be discussing separately. And there are actually 21 SFRs. Each has got different specific function to perform. We have specific SFRs for interrupts, for timers. We have these SFRs for timers. Then for serial communication, SBUF, SCON. Okay, and IE for interrupt, and all of them are located in register banks from bank 0 to bank 3. And let me tell you, all of them are in this RAM, internal RAM. Okay, So that's why I told you that we will be looking into the internal RAM organization once more. It is quite important, and we would be discussing that in a bit detail. All these SFRs are located in internal RAM, as well as the instruction sets are located in these internal RAMs. Okay. So with this, I stop here, and I'm stopping the recording.